Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In the last lecture, we started discussing the quantum mechanical solution of hydrogen atom problem. We defined hydrogen atoms Hamiltonian in terms of the kinetic energy and the potential energy, and the kinetic energy operator of the Hamiltonian atom, Hamiltonian for the hydrogen atom had a kinetic energy contribution from the nucleus and then the kinetic energy contribution from the electron. We replaced this kinetic energy operator, which had electron and nuclear coordinate dependence, to two one body problems, where the first one body problem was the movement of the center of mass. The second one was the kinetic energy and the potential energy of the internal motion of this hydrogen atom. When we say internal motion, we talk about the relative distance between the electron and the nucleus in the hydrogen atom. We then imposed a separation of variable for the solution of this internal Hamiltonian. We said that the eigenfunction of this hydrogen atom would depend on r, theta and phi, all three coordinates of the spherical coordinates, and then we said that let the eigenfunction be a product of a radial function and an angular function. We then used this variable separation process onto our Schrodinger equation of the hydrogen atoms Hamiltonian, and then we removed the angular component of the wave function, and we introduced a new effective potential which depended on the angular momentum of the electron. So, this is where we had. So, if you look at this wave equation, this has become actually a radial wave equation, because we have taken care of the angular part by applying the only angular operator that we had, that was Lagrangian, on the angular component of the wave total wave function. So, therefore, what we see here is that the hydrogen atoms Schrodinger equation has been converted to this new radial wave equation, where we have this effective potential, which is this, where we can see a Coulombic potential and a centrifugal potential. Together these two potentials, they provide the stability to hydrogen atom. Now, we would continue our discussion and looking at how we can solve this radial wave equation. We have this equation. Now, we take one we do one little exercise. What we do is that we divide the energy term E, which is a constant of this equation, in all these terms. So, you can see that my E term is divided here and the first term, and the second term I have divided 1 over E, but you would see why I have done that, but what I have done is that h bar square divided by 2 mu into 2 mu divided by h bar square. So, they essentially cancel out. So, at the end all I have is 1 over E, but we would see in a minute why I have written it in this way. This term we simply have h square by h bar square divided by 2 mu, and then the energy is there, and I have brought this E divided by E, that is 1 u of r to the left hand side, and I have written down this equation. Now, what we would do is that we would define a new variable, that is k square, as minus 2 mu E divided by h bar square. So, we would remember this definition. In particular, we will come back to this if I write down the definition of k. So, this is what it is. K is minus square root of minus 2 mu E divided by h bar. That is how you have defined k square. When I define this k square, you can see that this term becomes 1 over k square here, and then h square by 2 mu E, that becomes minus 1 over k square, and I have multiplied this 2 mu divided by h bar square into the Coulombic potential here. So, you can see that these 2 and 4 they have cancelled out. So, I am left with a 2 here. When I look at the second the centrifugal term, I see that h bar square 2 mu e has been changed to minus 1 over k square because of this definition, and then we have written down this equation. Now, we see that we have this equation in term written down in the coordinate of r. We now introduce another coordinate rho, which is given by k times r. If you check the dimensionality of k, you would see that k has the dimensionality of length inverse. So, when I multiply this k with r, I actually get this rho, which is a dimensionless coordinate. We have already seen the advantage of using a dimensionless coordinate in case of harmonic oscillator problem. So, again here also in this hydrogen atom problem also we are defining this dimensionless coordinate rho, which is simply multiplication of k into r, where k is given by this. When I do this, you see that I have, since rho is defined as k r. So, therefore, k square d r square is simply d rho square. So, these two terms have become d rho square, and here I have r k square. So, r k would give me a rho and I will be left with 1 k. So, therefore, this k rho is equivalent to r k square, and I have this r square k square converted to rho square. Now, I have simplified this equation. Instead of writing u as a function of r, I am writing it as u as a function of rho. The difference is that r is a dimensioned quantity, rho on the other hand is a dimensionless variable. So, here if we look, we have this term over here, and we will give a short name for this term. We call this term as rho 0, this term over here. So, that we have now this radial u wave equation in this simple form. So, I have the second derivative term over here. So, of u, which is now expressed in terms of rho, and now my differentiation is in terms of the dimensionless coordinate rho. Please remember, dimensionless coordinate is coming from by multiplying this k with r, and then I have this right hand side. So, what I have done in this exercise is that I have converted my radial wave equation corresponding from u of r to u of rho, and my equation is now written down in terms of the dimensionless coordinate rho. Now, the solution of this equation has been shifted to the solution of this. So, now we would try to solve this particular equation, which is the radial wave equation in dimensionless coordinate. So, we have this is the same radial wave equation that we derived in the previous slide. So, now we see we have some term in the left hand side or some term in the right hand side. I have this u of rho, whose form I would try to obtain. Once I know u of rho, and that will be the solution of this equation. The way we will solve this equation is that we would first break it down to its asymptotic solution. That means, it is the solution of this equation we try to find out when r, or the distance between electron and nucleus, are very large, and where r, that is the distance between electron and nucleus, is very small. In these two asymptotic region, we try to find the solution first, and then we talk about the solution of this equation in the middle region, in the intermediate region. First, we will discuss about the asymptotic solution at large r. So, that means, when r goes to very large value, that means r goes to infinite, since rho is defined as k into r. So, rho also goes infinite. When I write down this equation, you would see I am now using normal derivative instead of partial derivative, because I see that my equation, the differential equation has one variable, that is rho. So, therefore, I can write the normal differentiation here. this equals to the right hand side. When I look at the right hand side, rho has become very large. So, therefore, this term 1 over rho will become 0 and this term 1 over rho square would also become very 0. So, therefore, these two terms will become very small. So, therefore, I can ignore that and I will be left with this. Now, I have here a second order homogeneous differential equation whose solution I already know. What is its solution? It can have a solution of e to the power rho or e to the power minus rho. So, these two possible solution I would provide two constants a and b. So, that it tells that since I have these two possible solution, I would see which of the solutions are which of the solution contribute to my overall solution by what extent. This will be given by these constants a and b. Now, before we carry forward our discussion, let us consider first case when E is greater than or equal to 0, that means E is positive. If you remember, this k is defined as minus 2 mu E under square root divided by h bar and the rho is r into k. So, when I look at this solution for E greater than or equal to 0, I see the solution since E is greater than or equal to 0. So, E is positive and I have a minus 1 in the under the square root. So, therefore, this comes out as a imaginary root. So, I have So, these are the two solutions that I get when R is very large and E is positive. What do I see here? Here in this equation, in this solution, I see that I have an e to the power I r kind of term, which can be converted to a cosine function and sine function. This cosine function sine and sine function, even at very large value of r, they would still not become 0. They would also not become infinite, rather they would have a finite value, because this is the sum of a cosine function and a sine function which are bound between plus 1 and minus 1. So, therefore, this wave function even at large r, where r goes to infinite, would still not become 0, rather it will remain finite and it will show a sinusoidal and cosine oscillation. So, this wave function that I am obtaining indicates, you see, what happens is that when r is close to infinite, that means the electron is far away from the nucleus. So, these solutions indicate when the electron has completely left the field of influence of the nucleus, and this electron behaves as a free particle, free electron with no further interaction with the nucleus. So, that gives rise to positive or 0 energy of the electron, and the solution of that is unbound solution, because we cannot normalize this function, because this function does not become 0 at r equals infinite. So, this solution gives me to a problem of as the solution of free electron or free particle, and the solutions are unbound. I would now come to the other case where E is negative or E is less than or equal to E is less than 0. When E is negative, I see there is already a negative sign here. So, this term overall becomes positive and k is real. So, when E is negative, u of rho is a e to the power rho plus b e to the power minus rho. Here rho is now real, and when r goes to infinite, therefore, rho also goes to infinite, and since this is a real quantity, unlike this quantity where this is imaginary, that the nice thing about imaginary function is that even at r equals infinite, it will remain finite, but since rho is now real, you see when I have large value of rho, this function will diverge. this function will become infinite. So, I cannot have this as a solution to this my wave function. So, therefore, I will impose the condition that a has to be 0. So, therefore, u of rho is simply I am writing a proportionality constant, because there will be this is proportionality relation, because I have this constant over here. So, asymptotic solution for the bound state solution, that means even when we are discussing about those situations when r is large, but still the electron is under the within the influence of the nucleus. So, in those bound states, my asymptotic solution of this wave function will be e to the power minus rho. We will keep this in mind and we will go to the next limit, that is asymptotic solution when r is very small. Again, when r is very small, that means r goes to 0, that means the electron and nucleus are very close to each other. In that case, of course, rho also goes to 0, and my equation over here, the differential equation, the radial wave equation becomes, when I look at this term, the second term has 1 over rho, the first term is simple 1. So, when rho is very small, rho 0 by rho will be a very large term compared to 1, and furthermore, this third term, this term will be even greater than the second term and of course, the first term. So, therefore, when rho, the limit rho goes to 0, I have only this term which will become very significant compared to the other term. So, I keep only that term, and now I have this differential second order differential equation, where the function is u of rho and the coordinate that I am differentiating with is rho. The solution of this differential equation, we would not derive them, rather we would use them. It can have two possible solutions. One is rho to the power minus L, another is rho to the power L plus 1. These are the two possible solutions of this problem, and again I am just writing two coefficients C and D to define that both these solutions are possible, and which of the solution would contribute how much will be given by this C and D constants. So, this is the general solution for small value of r. Now, when I look at this term closely, I see that when rho is very small, this particular function rho to the power minus L. So, this is 1 over rho to the power L. So, when rho is very small, this term will become very large, or it will at rho equals 0, this term will become infinite. So, therefore, I would invoke that let this C coefficient become 0. So, that the contribution of this function is vanishing. So, that would leave me with this, that. So, now what I have obtained here is that at small value of r, where the electron and nucleus are very close to each other, the asymptotic solution will have rho to the power L plus 1 type of form, and earlier we had discussed when for asymptotic solution for large value of r, we had the asymptotic solution of this wave function u would become e to the power minus rho. So, this solution is asymptotic solution at small r, this solution is the asymptotic solution at very large r. Now, we will combine this information that we have and then write down this general equation, the general solution, which says that if you remember, we started our discussion by writing down this radial wave equation in terms of rho, which is the dimensionless coordinate here. we wanted to solve this equation. The way we solved this equation is that we first took its asymptotic solution at large values of rho and we got e to the power minus rho. Then we looked at its asymptotic solution at very small value of rho. We saw that the asymptotic solution would say gives us rho to the power L plus 1 a type of term. This is for one part of the asymptotic solution, this is for the small value of r, but what about the main body of the solution? The main body of the solution we still have to determine and we have given this name as V. So, this V of rho is still unknown. What we have obtained here is that the solution that we are proposing would have e to the power minus rho, rho to the power L plus 1. So, that the asymptotic forms of this solution is correct, is meaningful, but we are still left with solving this V of rho. That we can do. So, now you can see that we have a form for this u of rho. We can very well put this form of u in this radial wave equation, and you see that this requires a second level differentiation with respect to rho. So, if when I obtain d square u by d rho square, I would see that I have these 3 terms. So, I will have to take care of this complex differentiation, and then in the right hand side I simply have to multiply this. When I do this, I am not going to do that part. I would encourage you to use this solution of u in this equation and come down to this relation here. Look what we have here is that we have now a new differential equation which is expressed in terms of not in terms of u, rather in terms of v. How did we come to this position? We came here because we have obtained the asymptotic solutions of this u and we used this asymptotic solution into the radial wave equation and we have left with this v. Now, the angular momentum part is present. Rho 0, if you remember, we defined this quantity in terms of mu, energy, z and other constants of the problem. Now, if you look at this differential equation, you see that this is a second order differential equation in terms of v as a function of rho, which is the dimensionless coordinate. Now, the task at our hand has become that how can we solve this differential equation. But before that, we would find out we would have some discussion about what could be my v of rho. What is v of rho? V of rho is the main body solution of my hydrogen atom problem. This I am expecting to this function I am expecting to be a rather complex function, rather a complicated function, complex not in the sense of real and complex. I am expecting that this function will be a complicated function. What I would do is that I would start defining that let my v of rho be, I will express that in terms of what is known as a power series expansion. So, this is a series expansion. I am expressing my v, the unknown function, as a power series expansion. What do I mean here? You see, this is the general form where j goes from 0 to infinite. The advantage of this power series is that if you see the first term, so this is rho to the power j, it can be when it is 0, this is rho to the power 0. So, therefore, 1, when j is 1, this is simply rho, when j is 2, this is rho square. So, I am expressing this function v as a sum of a polynomial function where I can have rho to the power 1, rho to the power 2, rho to the power 3 and so on and so forth. The first term will be simply b 0, the second term will be b 1 rho, the third term will be b 2 rho square, the fourth term will be b 3 rho to the power cube and so on and so forth. So, this is what the power series expansion does. What is the advantage of it? You see, when I do not know how complicated my solution will become, it can be a very simple function or a very complicated function. But if I express this as a power series expansion, I have now a tool to allow to define this function in a functional form with no matter how complicated it becomes, I always have a higher order term that can be called in, and then we can express this particular complicated function. For example, when I truncate my series at the first level, I simply have a constant. When I truncate my series here, I have simply y plus mx plus c. If I go to the second order term, I can define a more complicated function. So, in this way I have the provision of defining any complicated function. So, if v is defined as this way, I can write down as dv by d rho is simply j goes from 0 to infinite j bj rho to the power j minus 1, because I am differentiating this function with respect to rho. Alternatively, I can write this equation as I replace j as j plus 1, since this is an infinite series, that will not have much of an effect. So, I replace j as j plus 1. So, therefore, j minus 1 has become j, and similarly I can write d square v by d rho square as j goes from 0 to infinite j into j plus 1 b j plus 1 rho to the power j minus 1. So, I am differentiating this term. So, now what, by defining v as a power series expansion term, I have dv by d rho and d square by d. Now, this is the differential equation I had. Now, I see that I have defined v here, I have dv by d rho, I have d square v by d rho square. When I have expressed them in terms of this b, bj's, which are the coefficients. When I use these relations in this equation, I would encourage you to do it. You would see that I will come to this relation, which is known as the recursion relation, that actually connects my bj to bj plus 1. In today's class, we have come to certain point in the discussion of our quantum mechanical solution of hydrogen atom. We have come to this recursion relation, and we will continue our discussion on this problem in our next class by looking at the solution of this radial wave equation. Thank you for your attention.